All right, so if you look at class example number 1 on page 527, part A, it says there's an evergreen tree, so a 6-inch evergreen tree is planted in June 2007. Okay, June 2007. And it has a growth rate of 15 inches per year. All right. So this tree gets planted. It's originally 6 inches tall. It's gonna grow 15 inches per year. 2 students are asked to determine the height of the tree in June 2018. So how tall will the tree be in June 2018? Okay, cool. So we can use arithmetic sequences to deal with this. So there's these 2 students and they have 2 different arithmetic sequences. To be honest, like the main difference here is Joel's T1 represents June 2007, right when the tree was planted, but Jenna's T1 represents June 2008 because it's like 1 year has passed. 1 year has passed and the 6-inch tree grew 15 centimeters to 21 centimeters. So it's like, honestly, it kind of just comes down to like, how are you gonna approach the problem? I don't think there's a wrong way of doing it here. I mean, like, if we look at Joel's approach, Joel has like T1, T2, T3, and we have 6, 21, and 36. This is June 2007, June 2008, June 2009. But at the end of the day, we'll still end up at the same result. So Joel has pretty much set it up like this. Jenna has sort of done it a little differently because she said that, okay, in June 2008, T1, because her initial term, her starting point is 21. June 2009, T2 is 36. June 2010, T3 was 51. So neither of these is like wrong. It's neither of them is like a bad way of setting up the problem, I think. But I mean, Jenna's is kind of leaving out some information, right? Jenna's just kind of Jenna's arithmetic sequence does not capture the info about the tree being 6 inches tall when it was planted. But that's not really a big deal, because I mean, it's also kind of nice to be like, after 1 year, the tree is 21 centimeters. After 2 years, the tree is 36 centimeters. After 3 years, the tree is 51 centimeters. So it's kind of like, I'm just trying to express that, like, it kind of doesn't matter how you do it. General term for Joel, well, basically what the general term means is we want to take our regular formula and we want to like replace all of the values that we can and then simplify. So replace values except n, except the variable n, then simplify completely. So the way we can do that, okay, so for Joel, the T1 is, so Tn equals 6 plus n minus 1 d. Oh, but d is 15 for the 15 centimeters. So then I can simplify. So Tn 6 plus, I'm just going to swap these so that you can see how I'm distributing. So distribute. So because it's a plus 15, so plus is plus, minus is minus. So Joel's general term ends up being -9 plus 15n. Maybe I'll say that as 15n minus 9. Jenna's general term. So we want to do the same thing where we take that original equation, but we replace all the values except the variable n, and then simplify completely. So Tn equals T1 plus n minus 1 d. Tn equals, Jenna's set up the sequence with the starting point of 21. And again, the common difference is 15. So then simplifying 15n minus 15. And, you know, Jenna's general term is going to make a lot more sense, because if we see how this works out, Jenna's general term is 6 plus 15n, where n actually represents number of years since the tree was planted. So this is a bit more clear. I feel that Jenna's general term is a bit more clear because n can actually represent like number of years since the tree was planted. So that's why these two general terms are different. N is representing different things in... It's hard for me to understand, like, it's hard for me to say what n is representing, because it's like n is representing like not how many years have passed, but like it's really just like the position in the sequence. It's hard to say like, oh, because that first day that the tree was planted, when it was 6 inches, a year hadn't passed. That was like day 0, right? So here n just kind of, it shows a position in the sequence, but it doesn't have as clear of a meaning. Over here, n actually means number of years since the tree was planted. So that's a nice little formula for us to use. Okay, so all of that to say, Jenna's formula kind of makes more sense to me because we can talk about n being years since the tree was planted. Okay, so going back to the original question, determine the height of the tree in 2018. Well, if it was originally planted in June 2007, I just need to see how many years until June 2018. So basically, it's going to be 11 years. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 years. So, you know, that's what we would expect anyways. Because 2018 minus 2007 is 11. So anyways, n has to be 11. So n equals 11. And then I want to plug this into the general formula, which was Tn equals 6 plus 15n. 6 Tn equals 6 plus 15n. Therefore, T11 has to equal 6 plus 15 times 11, because we take the n, Tn, that's what we replace in that general formula. And so that ends up being 6 plus 165 would be okay, so finally, part E, if the tree continues to grow, in which year will it reach a height of 28 feet? Well, remember, we have Jenna's general formula. And in which year, basically, we should solve for n. For n to find out how many years of growth are needed to reach 28 feet. So, all right, one weird thing is, we're talking about inches. So, conversion, 28 feet, and there are 12 inches per 1 foot. So that means I get 336 inches. So basically what I'm trying to do is solve for n when Tn equals 336. Okay, so 336 equals 6 plus 15n, gonna minus 6 on both sides. 330 equals 15n, divide both sides by 15, and I'll get n equals 22. So 22 years after 22 years after June 2007, that should be 2007 plus 22 is 2029.